Alright guys, we're going to talk about the forces between two current carrying wires today. So we've got this equation which we had before. So we've got the force on the wire is equal to the current through the wire times the length of that wire cross product with the magnetic field vector. Now it's important to note that this is the magnetic field on the wire. It's not from the wire, but on the wire. So and then one thing we're going to need to know also for this is what is the magnetic field generated by the wire. So these are going to be different things. So I'm going to say be from wire. And this is going to be very important when we talk about two different wires and how they exert forces on each other. So we have, this one is going to be mu naught times the current in that wire over 2 pi times the distance between those two wires. So this would be like if I have a scenario with a wire like this and like this. Let's call this I1 and this I2, and we'll say this distance is D. All right. Let's try and focus that camera a little bit. Should have paused it for that. Oh well. All right. So now I'm going to take this bottom wire. I'm going to make this bottom wire red actually, because I want to look at the field generated by this wire will also be red, and the field generated by the top wire will be black. So if we use our right hand rule for magnetic field from a wire, I'm going to take my hand and I'm going to wrap it around this bottom wire, my red wire. And so above the wire, the field is coming out of the page, but below the wire, the field is going into the page. So up here, I'm going to put a bunch of red dots. And make sure I put them around this wire, right? And I'm not going to put as many X's below because I'm not going to care about what's down here. I'm just putting them down here for demonstration purposes and for completeness. Now when I look at the other wire, my hand still goes the same way, right? It still curves that same way. So above the wire, I'm going to have dots. Below the wire, I have X's. So above the wire here, I'm going to just put them in between. I've got dots. And below the wire, I have X's for into the page. And X's down here. Okay, so now what forces do these wires exert on each other? Which direction are they going to be? Well, so for this bottom wire, this red wire, I actually want to look at the magnetic field from the other one. So I want to look at the black magnetic field in regular ink. So that's going to be into the page. So I'm going to take my hand and say my current is going to the right. So point my fingers to the right, my palm's into the page. So my thumb points up. So my force on this wire, which I'm going to use black because it's caused by the other one, is going to be up. Now for my top wire, my field is going out of the page, my current's still going to the right. So my hand should be, I can't get my hand that way easy, but my thumb should point down. So I'm going to use the red for that force and have that point down. So if current is in the same direction, the two wires are actually going to attract each other. Let's write that down. And if we want to do the same sort of drawing with the current going the other way, in just one of the wires, they're going to repel. Give me 1 second, I'll just draw that on pause. Alright, so I've drawn wire 1 and the magnetic field generated by wire 1 again. Now wire 2 is the one that I flipped, so it's now heading to the left. So let's look at the magnetic field from that guy. So I'm going to use my right hand rule. I'm going to say, well, my thumb's now pointing this way along the current. So my fingers are going to wrap around. So down here, below the wire, they're pointing up. But above that wire, they're pointing into the page. So they're the opposite direction they were before. So let's go ahead and draw that field. So down here, we're going to have dots. And up here, we have X's. Okay. So now once we look at the forces again, we say this bottom wire, okay, my wire is the red wire, but so I want to look at the field from the other wire on it. So I want to look at the black field. So my palm is going to go into the page because the magnetic field's into the page, current's to the left. So my thumb points down, and we are going to get a downward force. And in my other wire, my current is pointing into the page as well, and my current is heading to the right. So I'm going to have my hand like this, and my thumb points up. So we are going to get repulsive forces. So we'll say current in opposite direction wires repel. Yeah. So now, so we've got the direction. So that's just part of the force, right? Force is a vector, so you need magnitude and direction. So let's work on that magnitude part of it. We had those two equations up above. Let me slide this down just slightly so you can see those. Okay. And we need to figure out how to connect them. Well, the force on this wire is caused by the magnetic field from this wire. So let's make the notation that the force on wire 1 from wire 2, so I have 2 pointing at 1, is going to equal the current in wire 1 times its length times, well, the cross product of the magnetic field from wire 2 is going to be, that's the equation we have. Now, I can take this equation up here and put it into there. So it's going to look like I1L times, well, cross product, I guess, mu naught. If you're just doing the magnitude, you don't actually have to care about the cross product because it's going to come out the same as long as everything's perpendicular, which they are here. 2 pi times d, because we said the distance between them was d. So let's just say we're looking at the magnitude here, and let's just simplify a little bit to make this nice. So I'm going to get mu naught L over 2 pi, which will be a constant. And this technically, I guess, this L is the length of wire 1. So let's make a little notation there, because we're talking about the force on wire 1 from wire 2. And that's going to be I1, I2. So now it doesn't actually matter which order these two go in, because multiplication is commutative, right? I can switch it around, and 2 times 3 is the same thing as 3 times 2. And in the special case that I1 is equal to I2, if they have the same current in both, then that would give me the equation F is equal to mu naught L. Technically 1 still. So I should still call this 1 from 2 over, I forgot on this side I forgot the D. So let's put the D right here. Over 2 pi D times I squared. Alright, and that's how you're going to calculate the magnitude of the force between two parallel or anti-parallel wires. All right, we'll call that one a video, and I'll see you guys next time.